Okay, we've talked about linear systems. We talked about how do we determine whether or not a solution exists. We are now ready to introduce something called an eigenvector and eigenvalue. And the idea here is we're going to have a system of differential equations, and we're going to write them in the form as the derivative of our state is equal to a times the state. And A, we're going to assume, is a square matrix. If it's not a square matrix, the whole thing's going to break down. It's going to be a problem. But that means we're going to this problem would be recast in a different way. But for now, let's just assume this is the case. And we're going to play a game. Suppose I can find a vector we'll call it V, where if I take A times the vector, I get the vector back, but I scale it, so make it either shorter or longer by some value, and we'll call that scaling lambda. So this is a scary thing, so let's define this. So this is a square matrix. This is a scalar number, so just a single number. And these V's are vectors. And the idea is if I take a vector V, and when I take A times V, I get another vector, it's basically going to be in the same direction, but it's either going to be longer, stretched out, or squeezed in. So if absolute value of if lambda is bigger than 1, it's just going to stretch it out. If lambda is between 0 and 1, it's going to squeeze it in. And if lambda is negative, it's going to flip it in the opposite direction. Okay, and now so the question is why would we be interested in that? And the thing is, if I take e to the lambda t times a constant times v, and again, you should always stop and look at these things. So this is a scalar. And this is a vector. So this is all this is doing is taking the vector and either stretching it out or squeezing it in. If I look at this, first of all, its derivative is what? The derivative of this thing. So I'm assuming v is a constant vector. So this is just the derivative of e to the lambda t. So c is a constant. Derivative of e to the lambda t is lambda e to the lambda t, and we treat v as a constant. So that would be our left-hand side. If I take a times this thing, well, this is a scalar, so I can bring this out. And by definition, I'm assuming this is lambda v. So this thing and this thing are equal, which means that this right here is a solution to my differential equation. So if I'm trying to find a solution to this differential equation, finding things that satisfy this might lead to finding different solution. Okay. There are going to be times when this breaks down, but just as before, when it works, and you're done. If it doesn't work, that just means you go back and you do something else and try again. So let's define this thing. So we have this new thing. And the idea is we're given a square matrix. So if A is a square matrix, so this is something now we're given. I'm going to define something called an eigenvector. We'll call it V for now. And an eigenvalue, and we're calling that lambda. So this is a vector, this is a scalar. And what makes these things eigenvectors and eigenvalues is that it satisfies this relationship. And all this is saying is if I take A times the vector I get back is pointing basically in the same direction or the opposite direction, and it gets scaled by depending on what lambda is. And now the question is how do we do that? So we're going to go to this equation, this definition, and ask what does it imply? And here's going to be the thing to notice. Suppose V is an eigenvector. Now suppose I scale it and multiply by 2. Well, that 2 is a constant, so I can pull that out. And by definition, this would be 2 lambda V, or I can call this lambda times 2V. What does that mean? That means this is a solution to this equation, and this is a solution. So that means that if I have 2 solutions, I have to have infinite solutions, right? Because my options are either 0, infinite, or no solutions. And there was nothing special about 2. I could multiply by 2.3, get the same thing. So here's the thing that's going to be really important. AV equals lambda V is going to have infinite solutions. Okay, and we'll see this come back again later when we set things up. So, what the heck are we doing here? We're given a matrix A. We would like to find vector V and scalar number lambda that satisfies AV equals lambda V. Let me subtract lambda V from both sides. Now be careful, I'm working with vectors. If you forget your vector hat, your expressions are not correct, and that's an issue. So the precision here is vitally important, especially if you're trying to convey information or convey what you're doing to the reader. I cannot factor out a V here because this is a matrix and that is a scalar, and I cannot take A minus lambda. It doesn't make sense. I can only subtract matrices or subtract scalars, but I cannot take a scalar from a matrix. So here's what I'm going to do is I'm going to rewrite V, oops, sorry, this was minus, as I times V. Let me rewrite that. And now, so I times V is V, so this is the same thing, but that's a matrix, and that's a matrix, and they're both square matrices. So now I can factor out the V to get this expression. Now, just as before, I want to know what does this imply about solutions. Well, first of all, if V equals 0, then that is a solution. I am looking for values of lambda so that I get non-zero solutions to that. So again, what are my options are is one solution, no solution, or infinite solutions. I just established that there's at least one, so that's out. And my options are either one solution or infinite solutions. If V equals 0 is the only solution, that's bad. So I don't just want that. I need V not equal to 0, which means I need infinite solutions. If there are not infinite solutions to this equation, then everything has gone sideways and is not going to work. Okay, so we have A minus lambda I times V equals 0. I need infinite solutions. And the only way that's going to be true is if this matrix on the left has a determinant of 0. So what's going on? We are given A. That's the only information we have. I need to find lambda and V. So the game we're going to play is we're going to use this relationship right here to determine values of lambda. Okay. And by the way, if we have an n by n system and we want to find a solution to the differential equation, we're going to need n solutions. All right. So let's just write all this out. So we're assuming at this point we have differential equation. So we know A. We are looking for solutions, and we know that they're going to look like C times e to the lambda t v, where AV equals lambda v. And we just decided that that implies that the determinant of A minus lambda I has to be 0. So the way the game is going to proceed is the following. So we're assuming we know A. The first thing we're going to do is we're going to solve this thing for lambda. After we do that, we're going to determine the eigenvectors. These are the V's, where A minus lambda I H VI is equal to 0, and VI is an eigenvector. Now we got to be careful here. This is only going to work if A is an n by n matrix. It's only going to work if we have n eigenvectors. Okay, and these have to be independent. And the reason for that is x of t is going to be a vector with n components. So I'm going to write it as a sum of these eigenvectors and the only way that I can find a solution, or can be guaranteed a solution, so I've got n unknowns here, I would like there to be a solution no matter what my initial starting point is, which means I'm going to have n of these vectors to guarantee that I can solve the system equations for C1, C2, all the way out. Okay, let's look at one example, and then we'll move on after that. So for example, suppose I have the differential equation that looks like this. So the matrix is 12 minus 10, 15, minus 13. I want to find eigenvectors and eigenvalues. So my first step is take the determinant of this thing minus lambda times I. Since it's 2 by 2, my identity matrix is 1, 0, 0, 1. And this has to be 0. So this is going to be, so I'm going to get 12 minus 10, 15 minus 13. If I multiply the scalar through, I get lambda 0, 0, lambda. And now when I subtract these two matrices, notice the only thing I'm going to have for the right is entries on the diagonal, and that's always going to be true because of the identity matrix. I have 12 minus lambda, minus 10, 15, minus 13, minus lambda. So this has to be equal to 0. And now since it's a 2 by 2, I can just use my definition of the determinant. It's going to be multiply the diagonal entries together minus, and then I multiply those off-diagonal pieces together. So I get this expression, and now I'm just going to grind it out. So let's see. This is going to be 12 times minus 13, so this times this, minus 12 lambda. And I'm going to have minus lambda times minus 13 is plus 13 lambda plus lambda squared. So basically I just FOILed all this out. And this is going to be plus 150 is 0. So I've got lambda squared. 13 lambda minus 12 lambda is plus lambda. Oh gosh. Let's see, let's 12 times 13. This is going to be 36, 12, so that's 156. So minus 156 plus 150 is 0. So I get lambda squared plus lambda minus 6 is 0. I've got a quadratic. If you don't immediately see how to factor it, just go straight for the quadratic equation. Don't waste any time. In this case, I believe I can factor it. So it's plus 3 minus 2 gives me that. 3 times minus 2 is minus 6, so that works. So my eigenvalues are either minus 3 or 2. And I've got 2, and I need 2 because I've got a 2 by 2 system. So I'm feeling really good about this so far. All right, so what did we have so far? So in our example, we started off with the linear system given by a matrix of 12 minus 10, 15 minus 13, x. We decided that we have eigenvalues of lambda equals, we'll call that lambda 1 is minus 3, lambda 2 is 2. Now I got to figure out what my v's are. So first question is, what is v1? So I'm using this. So for v1, I've got a minus, my lambda is minus 3i times v1 is the 0 vector. So this is going to be, what, 12 minus 10, 15 minus 13. This is going to be minus a minus. Then 3i is going to be 3003. v1 is 0. So 12 plus 3 is 15. Minus 10 plus 0 is minus 10. 15 plus 0 is 15. Minus 3 plus 3 is minus 10. So I need to solve this linear system, and we are in luck because we know exactly how to solve these things. I can now put this into my augmented matrix. So notice this 0 is a 0 vector. So that vector becomes that. And now I immediately see that if I take row 2 and subtract row 1, so I leave the top row alone, I get 15 minus 15 is 0, minus 10 plus 10 is 0, 0 minus 0 is 0. So I'm going to have infinite solutions, which I expect if that does not happen, you did something very wrong. And I have 15x minus 10y is 0. So I'm assuming my v1 is in this form. So what does this say? This says then that 15x equals 10y. So x equals 10 15ths y, or 2/3 y. So my v1, so x is 2/3 y, and leave y alone. So my v1 is basically this vector 2/3 1, but I can stretch it and pull it any way I want, and it's still going to be an eigenvector. Okay, so I have lambda 1 is minus 3, v1 is any number times 2/3 1. Okay. So again, this is my differential equation. I now have lambda 1 is minus 3, and its eigenvector is any number times 2/3 1. Lambda 2 is what we say was 2. And I want to figure out what 2 is. So I'm going to look at A minus lambda I, V equals 0. So A is 12 minus 10, 15 minus 13, minus 2 times the identity matrix, times V2 is 0. So I'm going to have 12 minus 2 is 10. Minus 10 minus 0 is minus 10. 15 minus 0 is 15. Minus 13 minus 2 is minus 15. Assume that V2 is some xy. And that is 0. So I can put this in my augmented matrix. This is kind of ugly. Let's do this. Let's take 1/10 times row 1 would give me 1 minus 1 is 0. And 1/15 of row 2 would give me 1 minus 1, 0. So now if I take row 2 minus row 1, leave the top row alone, I get 1 minus 1 is 0, minus 1 plus 1 is 0. So I basically get that x minus y is 0, or x equals y. So my V2 is xy. We just said x is equal to y. So my V2 is any number times 1, 1. And again, if you get a unique solution, or you don't get any freedom here, or you need to get infinite solutions, you've done something terribly wrong. So my eigenvectors are lambda 1 is minus 3, V1 is any number times 2/3 1, and the other one is lambda 2 is 2, and V2 is any number times 1, 1. Which means then my solution to my differential equation is going to be any number, we'll call it C1, times e to the minus lambda t, in this case lambda is minus 3, times this vector, and then the other one is going to be C2 e to the 2t, because that's my lambda, and that's any number times 1, 1. So my solutions look like this. And just as before, you should be able to look at this and explain the stability or the overall behavior, right? This is going to go to 0. So this term goes to 0. But this is growth. It's exponential like e to the 2t. So we would expect solutions to this thing to grow like e to the 2t.